Thank you, Laura, and welcome to all in attendance this afternoon. It is our pleasure to present today's Water Resource Recovery webinar, The Phosphorus Problem, Treatment Options, and Process Monitoring Solutions. Recent events have demonstrated that excess phosphorus in receiving waters can create many serious problems. For this reason and others, incorporation of new and more restrictive phosphorus limits into discharge permits is occurring in many states. Many facilities will need to add a process to the flow sheet. This webinar will help you to answer the questions about which treatment methods are right for you and how process monitoring can help you to achieve the required performance at the lowest cost. So what is phosphorus? It's more than just the letter P, which is how I'll refer to it throughout the webinar. It's essential to life. All living organisms require it. There are no substitutes for it. It's a major component of fertilizer for plant growth, but it creates nuisance conditions in excess. And typically it is thought of as the limiting nutrient in fresh water, nitrogen being the limiting nutrient in marine water. And also, and a subject of a different webinar, high-quality reserves are depleting, such that in a few years we could run out of quality phosphorus. But that's, as I said, that's a topic for another day. So P promotes growth of algae. Excessive algal growth has many undesirable effects. Human health has been demonstrated recently. Drinking water can be made unsafe. Environmental. Fish kills and such degrade the environment. And economic. Limited access to recreation waters and the properties around them has a terrific negative impact on their economic well-being. How does P get into surface water? The two main ways are through diffuse sources such as runoff from agricultural fields and point sources, that is water resource recovery facilities that discharge into streams, lakes, and rivers. As far as regulation of P and point source discharges goes, there are three types. There are technology-based limits, typically 1 milligram per liter total phosphorus at a monthly average. There are total maximum daily loads. These are mass-based limits. Unique thing about this, as treated water flow increases, the concentration you achieve must decrease. And water quality-based emission limits. These are numeric concentration limits applied statewide typically to not cause adverse effects. And that is what we're going to talk about a little bit more depth in the next two slides. So if we look at the status of numeric nutrient criteria in the 50 states, the current status depicted here, the states in white have no N or P criteria. The states in light blue have some waters with N or P criteria, and then as the blue gets darker, more water types with more criterion up to the level purple. Level purple is complete set of N and P criteria for all water types. Looking ahead to 2016, more states get into the blue territory and many get a darker blue. For example, Ohio and Vermont both have a full, complete set of N and P criteria for all water types in 2016. Taking a look at one state, Wisconsin, as an example, they have defined adverse effects threshold depending on the surface water type. So the P criteria depend on whether you're discharging into a river, a stream, a reservoir, or a lake. And these concentrations are in micrograms per liter. So 1,000 micrograms per liter is 1 milligram per liter. So quite low effluent limits could be required in these examples, with lakes going down as low as 15 to 40 micrograms per liter. Well, what are you going to do? There are several options for complying with P limits. Variance based on economic feasibility, basically too great of an economic burden to your ratepayers. There is water quality trading, basically trade with your neighbor or with a nearby entity to offset the limits. Adaptive management is watershed based, and the idea there is to restore the stream to water quality based criteria so that limits aren't needed. And then the topic of the rest of today's webinar, operational changes or add chemical, and that is improving your treatment process to meet the treatment limits. Wisconsin has identified that significant upgrades to the treatment facility will be likely if the WQBEL is less than 0.6 milligram per liter. And a compliance schedule is being granted, and it will extend 5+ years, but not more than 9 years, to enable utilities a chance to construct the necessary facilities. Well, that's some background on phosphorus and the regulatory issues. Let's move along on into phosphorus removal treatment options. But first, I want to bring up some terminology. P, as I've mentioned, refers to phosphorus in general. TP is total phosphorus, particulate plus dissolved phosphorus, and important to note that that is typically what discharge limits are defined in terms of. Orthophosphate, on the other hand, is the monitoring parameter. It is the dissolved phosphorus with the chemical formula PO4 with a -3 charge. Biological phosphorus removal, or enhanced biological phosphorus removal, introduces some additional terms, starting with Oxic, and that's the same as aerobic, and that's where you have a DO of 1+ milligram per liter. Anoxic is a condition where DO is not present, but nitrate is available, and anaerobic is defined as no DO and no nitrate. So with that terminology out of the way, let's talk about how is P removed. And there are two ways. It can be done biologically or chemically. The basic concept in either situation is that the dissolved P is made to particulate P, and that is settled out with the rest of your sludges and removed with waste sludge. Although most water resource recovery facilities are not designed to remove P, some P removal occurs naturally. So on the left-hand side here we have a typical influent phosphorus, total phosphorus, and better than half of it is in the particulate form, and the rest of it is in soluble or ortho-P form. Naturally, during biological transformation, secondary effluent then will consist the soluble P, mainly of soluble P, and the particulate P portion will be greatly reduced. Some of that particulate P, though, will be removed from the treatment system in the waste-activated sludge. In order to achieve even lower limits, though, additional treatment steps for enhanced biological phosphorus removal or chemical P removal are required. In this case, converting more of the soluble P into particulate P, which is then removed with the waste sludge. Let's start with chemical removal. How it works. Well, addition of ferric or alum to water triggers a complex chain reaction, as depicted in this model. So iron or alum is added to the water, and the soluble P gets mixed up with these hydrous metal oxide, or HMO, precipitates. Some of it is absorbed, and that absorbed P can then be removed. And this is a very young ferric hydroxide flock, 1 minute old. Isn't he cute? So the relationship between dosage and ortho-P is shown in this figure here. On the vertical axis is the dissolved P target from 0 to 2, and on the horizontal axis is the ratio of iron to phosphorus needed to achieve that target. And if we take the model prediction, we see that at relatively high targets, a relatively lower amount of iron is needed compared to the amount of P. But as you get lower, lower and lower, that proportion increases. The second line here is for plant data, and this plant data is reflects possible inefficiencies in the system, for example, inefficient mixing of chemical with the water, and it displays an even greater proportion of metal needed to remove P, so that looking at a limit of 1, for instance, mostly that P is absorbed to the surface of these HMO precipitates, and you get relatively lower sludge production and alkalinity consumption. But as lower targets are pursued, in addition to the surface reactions, there's co-precipitation and other competing reactions such that there's increased sludge production and alkalinity consumption in addition to the greatly increased amount of chemical required. There are multiple chemical P removal control strategies available, starting with pre-precipitation, and in this case the chemical is added upstream from the primary clarifiers and the P is removed with the primary sludge. In simultaneous precipitation, the chemical is added to the activated sludge process, either upstream of the aeration tank or upstream of the final settling tank, and the P is removed in the waste activated sludge. Post-precipitation involves adding iron downstream from the final settling tank to be removed in the sand filter or a tertiary clarifier. In either case, often the P will end up being recycled back to the primary sludge. And in order to achieve the lowest limits, multiple dosing points will likely be required. Let's take a closer look at enhanced biological phosphorus removal. In an ABPR, an anaerobic zone is required in which bacteria take up BOD in the form of VFAs and build that VFA into something called a carbon, something called PHB. And in the process they release ortho-P into the water. This is the feed condition where the battery is charging. Continuing with the battery analogy, the battery discharges, that is the PHB is oxidized in the aerobic zone. And in the course of doing this, the bacteria retake up the ortho-P that they released and also take up excess ortho-P to prepare for bad conditions that they recently already observed. The P then is removed when waste sludge is wasted from the system. The P content of biological sludge could be as high as 8 to 10% compared with a typical activated sludge, which is around 2%. This works because the energy released by the PHB oxidation is much greater than the energy required to store the PHB, so that the bacteria that can do this have a competitive advantage. Let's take a look at a typical anaerobic oxic process configuration. The chart on the top shows a bioreactor with the anaerobic zone on the left and the aerobic zone on the right. The chart on the bottom shows concentrations in the bioreactor on the vertical axis and location corresponding to the picture above in the bioreactor on the horizontal axis. So in the anaerobic zone, ortho-P is released, and it is probably 3 times or more the influent ortho-P concentration. Subsequently, in the aerobic zone, that ortho-P is taken up. The BOD then is stored into PHB in the anaerobic zone and then oxidized in the aerobic zone, such that the net P removal then is the difference between what came in and the P remaining at the end of the aerobic zone. The 3 requirements for biological phosphorus removal are: 1, you need excess phosphorus; 2, you need readily degradable carbon; and 3, there must be cyclic, anaerobic, and oxic conditions. These 3 conditions provide what is needed for these bacteria, known as phosphate accumulating organisms, to be maintained in the system. So moving past the treatment removal options, let's look at some of the monitoring solutions. So to begin with, there are, to date, phosphate is measured only through traditional wet chemistry methods, such that orthophosphate cabinet analyzers are the state-of-the-art today, whether or not you're using chemical or biological removal. And these all rely on wet chemistry, as I mentioned, and there are four main components to an analyzer. Electronics, photometer with tubing, sample transport, and of course reagents and solutions. Features of an online analyzer. Desirable features are low reagent consumption to save money, suitable for outdoors so the analyzer can be located anywhere in the process where it's needed, automatic calibration to ensure that you are assured of the accuracy of the measurement, an integrated permeate pump, and a filter module that allows you to withdraw a sample directly from the mixed liquor. So monitoring for chemical P removal is addressed in this slide. The first attempt usually is in the effluent, monitoring the effluent phosphate to help you understand how well your treatment process is performing. But in order to get a better handle on proper chemical dosing, some feedback control may be needed. And in the case of pre-precipitation, locating a phosphate analyzer in the primary effluent could give you the feedback you needed to dose chemical in the primary effluent. With simultaneous precipitation, these locations for phosphate analyzers, either between the aeration basin and the final settling tank or after the final settling tank, to measure the phosphate concentration to give you the information you need to add chemical to secondary treatment. And with post-precipitation monitoring in the effluent to adjust the chemical dosing upstream. Another way is to measure the phosphate coming into the treatment plant through the primary influent or primary effluent, and then dosing the chemical needed to match the demand from the influent phosphorus. Watertown, Wisconsin has recently incorporated a phosphate analyzer into their treatment simultaneous precipitation treatment process. Chemical dosage point is between the aeration tank and the final settling tank. The chart on the left is a screenshot from their SCADA system showing the phosphate concentration from the analyzer in blue and the pump speed, the chemical dosing pump speed in green. And when the phosphate is below the set point concentration, the pump speed is at minimum until the phosphate exceeds the set point concentration, and then gradually the pump speed is ramped up in order to reduce that phosphorus. At some point, when the phosphate again starts to decrease, the pump speed decreases accordingly. This enables them to more closely match the chemical demand that they have for phosphorus removal. And the chemical cost reduction is shown in this slide. The analyzer was installed in 2012. It is a 3 mg/GD facility. Their limit is 1 milligram TP per liter for now. Ferric chloride costs are shown here starting in 2011 and 2012 before full implementation of the analyzer, and they cost for around $90,000 per year. In 2013, costs were reduced to just over $60,000, and 2014 to date, costs have been less than $40,000. The analyzer paid for itself in 1 year and plus had other benefits, including decreased sludge production. So now to talk a little bit about EBPR monitoring. And when it comes to EBPR, everything is important. COD, BOD, dissolved oxygen, nitrate, TSS, ORP, blanket depth. Taking a look at biological P removal, orthophosphate release and uptake with a phosphate analyzer. So an analyzer in the anaerobic zone enables you to assess phosphate release and maybe make adjustments, adjust mixing, or activate a swing zone if additional anaerobic volume is needed. An analyzer in the oxic zone gives you information on phosphate uptake. And taking a little closer look at phosphate uptake, P uptake is rapid when conditions are right. These are not online measurements, these are grabbed samples, but it illustrates the point that phosphorus is rapidly taken up. The ortho-P concentration is on the vertical axis, and along the horizontal axis is the percentage of the total aeration volume. Pretty much all uptake is complete by halfway through the aeration volume. Well, it looks easy, but let's take a hypothetical look at what might not occur if you have too low DO concentration in your oxic zone. So in this case, the ortho-P concentration again is on the left, and ortho-P release is shown in the anaerobic zone. It's the black line, and then the orange line is the P uptake in the aerobic zone. Incorporating baffles and staging the air so that more air goes to the front of the oxic zone may enable you to achieve even greater uptake in the initial portion of the oxic zone and overall greater TP removal. Another monitoring parameter that has been utilized for EBPR is ORP. This chart here illustrates how an intermittent aeration system might perform. And the chart is a little busy, but I'll walk you through it. So looking at ORP on the vertical axis, actually it's millivolts over 30, so it's scaled. And we see that when aeration is first turned on, the ORP increases to a point and then levels off. And this leveling off occurs right about at the point when the ammonium concentration is near zero, as shown by the blue triangles. On the other end, after the aeration has been turned off, the ORP decreases gradually and then does level off to a point called the nitrate knee. And this nitrate knee occurs at a point when nitrate is nearly exhausted. At this point, phosphate release can proceed. Taking a look at a chart from ORP control of intermittent aeration, this again is another busy chart, but again I'll help step you through it. The two parameters I want you to keep an eye on are the red line, which is the ORP, and the blue line, which is the airflow. We see that the blue line, the airflow, goes to zero, and the red line decreases as it did in the previous chart until it hits the nitrate knee. That nitrate knee triggers a timer which allows a suitable amount of time for phosphate release. When the air turns back on again, the phosphate or the ORP increases and the cycle repeats itself over and over again. So the role of SRT to biological removal cannot be understated either. If SRT is too low, there is not enough time for these phosphate accumulating organisms to exist in the system. They are washed out. But too high of an SRT also has detrimental effects. Secondary release, for example. As the sludge gets older, more decay occurs, and when this decay occurs, the phosphate that they had worked so hard to accumulate is released back into the tank. Competition. There are bacteria that are able to store these carbon products but without the release of phosphate, and they may outcompete the PAOs, which is also not desirable. Lastly, but not least important, is settlability. This chart helps illustrate the importance of sludge settlability to P removal. It shows the effluent particulate P on the vertical axis and the effluent TSS on the horizontal axis. Multiple lines are shown. Each line represents a sludge with a different P content, such that the blue line, the 2% P, is typical for activated sludge, and 8 to 10% P might be observed in an enhanced biological phosphorus removal system. Even at an effluent of 10 milligram per liter TSS, that equates to 0.5 milligrams per liter of particulate P. Of course, that particulate P, when added to the dissolved P, is the effluent TP, such that this treatment plant could not expect to achieve any lower concentration than 0.5, even if their soluble ortho P was 0. So, what is the process control strategy for achieving the lowest effluent TSS? Well, this chart, which was has been taken from a WEFTEC paper presented at the 2013 WEFTEC, shows the effect of SRT control and sludge blanket control. On the vertical axis is the effluent total suspended solids, and the horizontal axis is time over a period of many months, several years actually. And before the new process control strategies were implemented, as shown at the black arrow, the effluent TSS was high, relatively high, and very inconsistent and variable. Following implementation of these strategies, the effluent TSS became much lower and much more consistent. This concludes the presentation. I will leave this slide up here with some further reading for you to get more details. The WRF report, many utilities in attendance today no doubt are subscribers to WRF, and WRF reports are available free to you for download. I encourage you to download, read, and get more information. So, very pleased to take your questions at this time.
Thanks, Rob. Very informative. We've had a couple comments throughout the presentation. Some of you guys had difficulty hearing what others were loud and clear. So I apologize if any of you guys had any issues hearing Rob's presentation, but the link to the video, the recording should come in clear for you. So we will follow up with that, and you should be able to hear it clear via the recording at least. A lot of it has to do with connections. So again, I apologize about that. Let's go ahead. And a lot of questions came in over the course of the last 30 minutes. And there's a couple questions that are kind of tied together. So this is kind of a two-part question for you, Rob. One is, what is the benefit of feed-forward control, and how does it differ from feedback control? And the second part of that question, I'd like to tie these two together, is have you ever used both feed-forward mass pacing with feedback control?
Good question. Yeah, so the benefit of the benefit of feed-forward control is the lowest possible chemical consumption by perfectly matching the chemical dosage to the chemical requirement. It differs from feedback control in that you're monitoring upstream from the dosage point, and you also require a model to predict what that dosage should be. Whereas with feedback, you're merely increasing or decreasing the dosing rate due to with the feedback from the analyzer. As far as using them together, typically feed-forward control would be used also with some feedback control as a trim. Models are not perfect, as we know, and the feedback control would eliminate the errors in the model.
Great, thanks, Rob. Next question. What operating adjustments are possible to improve the performance of biological pee removal?
Well, it seems like there's not a lot that can be done, but actually there are several things that can be done. And the first thing is to protect that anaerobic zone. If the anaerobic zone is not large enough, it will limit the ability for phosphate release. So reducing the mixing, for instance, if many plants use coarse bubble air for mixing, to not put dissolved oxygen into the water will help. Also, for plants that have that, a swing zone. So basically, if more anaerobic volume is needed to generate VFAs, a swing zone can be opened up to allow the anaerobic volume needed to also release phosphate. Those are just a couple things that can be done for the anaerobic zone. For the uptake portion of it, of course, increasing the aeration rate in the initial oxic part is very important. So if I didn't mention it, but if the phosphate uptake, basically it represents an opportunity lost. When the uptake does not occur in the initial oxic part because of insufficient DO, many times there's no possible way to catch up. So that it represents an opportunity lost and a limit to the amount of phosphorus that can be removed.
Thanks, Rob. There were a couple comments that I was not coming clear. I apologize. The second question that Rob answered was what operating adjustments are possible to improve the performance of bio-P removal. The first question, which was a two-part question, dealt with what is the benefit of feed-forward control, how does it differ from feedback control, and can you use them in conjunction with each other? The next, we have a lot of questions coming in. We'll try to get to as many as possible. The next question I would like Rob to address is, can chemical and bio-P removal be employed together?
Well, the answer is yes. But if you are doing biological P removal, it is very important to limit the chemical addition as much as possible. Because remember, these bacteria, these PAOs, rely on excess phosphorus in order to survive. And if you take away that phosphorus, it reduces their competitive advantage. So what might be a practical strategy is, for example, adding chemical to return streams. Centrate, for example, may have high concentrations of phosphate, or adding chemical at the very end of the process to remove the phosphate further than what the biological process might be able to do alone.
Great, thanks, Rob. And this is a follow-up to that one. Can we, or how do we, quantify the reduction in sludge between chemical P removal and bio-P?
So the question is, how do we quantify the reduction between bio-P and chemical P?
Correct.
Well, I guess the ultimate measure is the effluent total phosphorus. But as far as in the process goes, if I understand the question correctly, with chemical, it's the process monitoring, and of course, if you use a feedback strategy, you will have a phosphate measurement downstream. With biological, you've got two things to measure, and that is the phosphorus release and the phosphorus uptake. Measuring the phosphorus, the phosphate in the oxic zone will enable you to find out if the uptake is sufficient, but if you still have relatively high levels, you will need to also do some monitoring of the release, because if the release is not sufficient, the uptake will not be able to make up for it. I think that answers your question, but if it doesn't, please restate it or ask it again, and we'll try to address it the way you expected.
I like it. Stump the doctor. I'm going to throw him an easy one now. What are the values of ORP that indicate BioP release versus uptake?
Well, that is seemingly an easy question. The trouble with ORP is it's a relative measurement, and so every facility, every application will be different. But in general, the values indicating biological phosphorus release are negative 100 to negative 250 millivolts. This could be more or less for your facility. As far as uptake goes, certainly it needs to be in the positive range, so plus 25 and higher.
Okay, Rob, we did get clarification on that last question. It's more about the sludge production, not quantifying where the P is removed by which process. So a clarification to that last question was, what is the sludge production for chemical P versus sludge production for BioP? Thank you for sending that back in.
Yeah, thank you very much. Yes, that actually makes perfect sense now. Chemical P removal will certainly increase sludge production. There's no way around it. However, it might not be that. It might only be a marginal increase if your limit you're trying to reach is 1 milligram per liter. Certainly, as lower limits have to be reached and more chemical has to be added, there's more competing reactions, additional sludge will be generated. I am not aware of studies indicating that biological P removal increases sludge production. So I would expect that the sludge production would be the same or possibly even lower than, say, a conventional activated sludge system. One complication, though, is that sludge is, I don't want to say unstable, but if it's not handled correctly or stored properly, bio-release of that phosphate will occur, and when you decant or when you dewater, that phosphate will come back into the treatment plant. So that's really the complication with BioP sludges.
We have one question coming in relating to the online analyzer. Does it monitor P, total P, or orthophosphate?
Yeah, good question. So the analyzers that we have talked about today measure only orthophosphate, and that is the dissolved component. And the reasons for that are that it is really the function of the ortho-P is really, removal of ortho-P is really the function of the process. So when you're adding chemical, you're converting ortho-P to total P. When you're doing EBPR, the objective is to put that ortho-P into the biomass. Total P, on the other hand, is a compliance parameter, and so it would be useful on the effluent end of a treatment system. And there are analyzers that do that. The complication is that you need to digest those solids, so it's another additional cost, another component, another complication to the analyzer, which is just not needed for process monitoring.
We have a few more minutes, so we'll just run it to the end because the questions keep coming in. The next question is, biological removal seems a lot more complicated. Why not just use chemical?
Enhanced biological phosphorus removal is very complicated, but facilities can learn in time how it's done most effectively, and I've seen this happen in my own experiences in consulting. Plants get better, but the problem with chemical, though, is although it is simple it's simple to add chemical, the effects are that the cost of the chemical, for one, alkalinity consumption another, especially as you're trying to get to lower and lower effluent, more and more chemical is needed, and it could harm the nitrification process, which is a real problem. But also, as we've already talked about a little bit, is the sludge production. Increased sludge production, and not only the total amount of sludge, but also the amount of inert solids. So if you're doing simultaneous precipitation, you're carrying additional inert solids in your mixed liquor. So that instead of having to carry a 4,000, say, for a mixed liquor that's 75% volatile suspended solids, you might have to carry 4,500 or 5,000 just to get the same amount of volatile suspended solids.
Not sure. So this is a typical. I'm not sure, but we'll see if we can answer this one for you. How many cycles are typically required to achieve 0.6 milligrams per liter concentrations in typical municipal wastewater streams? How many cycles?
Well, I guess I'm going to rephrase that question for you, and if I do it wrong, please let us know. So you're talking biological phosphorus removal here, and you're wondering how many times that has to go through the anaerobic zone. And I don't have a number for that. But what I do have is there's a certain hydraulic retention time, so a straight calculation of hydraulic retention time of maybe 1 to 2 hours, and the SRT for total SRT for biological phosphorus removal is 7 to 12 days, and of course only a fraction of that is anaerobic solids retention time. So although number of cycles could be calculated, I think if my answer doesn't suffice, let us know, and we'll reply and follow up.
Okay, I'm going to get as much out of Rob today as possible, so we have 1 minute left. Last question. How does someone choose a chemical removal control strategy?
There are a lot of choices, and I can relate my original experience with this when I was an intern at the City of Toledo Bayview Wastewater Plant. They added the chemical to the grit tanks upstream from the, they had aerated grit upstream from the primary clarifiers, and I thought that was the only way it was done, and it seemed to make the most sense. You know, you took some of the because the chemical takes some of the additional BOD out of the water, and you don't have a lot of, seems like you would have fewer competing side reactions. But actually, simultaneous precipitation has advantages as well. And actually, there are fewer competing reactions in simultaneous precipitation, and there are a significant amount of TP present as soluble TP available for removal. So possibly a lower chemical dosage. Post-precipitation, on the other hand, is probably going to be only suitable for those that have very low effluent soluble P, and mainly the reason is, if you don't already have it, is the need to add a tertiary unit process. So high capital cost.
Great, Rob. Thanks. That takes us to the end of today's webinar. I really appreciate everybody attending today. You know, we had really good attendance and everyone stuck through to the end. I really appreciate it. So hopefully you found this information valuable. Please fill out the short exit survey on your way so we can continue to provide interesting topics and valuable information to you. And of course, we will be at WEFTEC in a couple weeks, so I hope you stop by and visit us and speak with Dr.